Can you see the presentation? Hello?
Yes, sir.
Okay. So let's start. Now, so far we have been discussing the field programmable analog array, the basic analog building block for making this field programmable analog array. Now, our intention is to design a processor which will be based on mixed signal processing, where analog digital both will be there on the same chip. Now, concept of analog processor is a bit new, and we have introduced that concepts. So our intention is to design a processor where analog processor and digital processor simultaneously both will be working and will be in the same chip. Now, if we just talk about analog processor, then definitely concept of analog memory comes in, and that we have to understand what analog memory is. So today we will be discussing that. Now, analog memories, still it is in the research stage, but some components are also coming in the market, and the concept of analog memory is a bit stable now, even though a lot of research work still is going on. But analog processor is a new concept which we are going to introduce here. Now, what is analog memory? In simple word, it is the device which can store analog information. Now, what is analog information? How it will be stored in the memory? Now, here the interesting thing is analog data is continuous. So how it will be stored in the memory? For an example, let's say if a signal lasts for 3 minutes, say, for an example. So how these 3 minutes information can be directly stored on a memory? Now, as we understand, memory means there will be some locations where some data will be stored. That's what we are familiar with the digital memory. There will be address which define the location of the memory depending on the number of address lines. Say if there are n bit address lines, there will be 2 to the power n locations, and in each location number of bits will be employed to store the data. That's what for digital memory. But for analog memory, there is no concept of bit to how the data will be stored. Here one concept is like that. Any analog signal, but is a continuous time signal, can be sampled into a finite number of information. And how it will be sampled? That is governed by Nyquist sampling rate. That means if the bandwidth of the signal is f, then sampling frequency will be greater than or equal to twice f. We all know all these things, Nyquist sampling theorem. So based on that, we'll be sampling the analog signals, say after a regular interval, capital T, where capital T is the sampling time or sampling period. So that means if we sample a finite number of signals, so those signals are still discrete analog signals. So if you see in this diagram here, left hand side is a continuous time analog signal and right hand side is sampled analog data. So like 0, 1, 2, 3, 4, these are the sampling number. So n is the x-axis and yn, and xn is the y-axis. So xn represents the value at sample number n. So these values are discrete analog. So how analog signal will be stored? We all know that analog signal can be stored in a capacitor, because capacitor is basically charge storage device, and this well-known formula we know, Q equal to C into V, where C is the capacitance. So this concept will be utilizing for storing analog data. And like if you see this diagram, in this diagram here there are 3 transistors. Now there are one horizontal line, one vertical line. Let's consider this one line is for writing data and another line is for reading the data. And there are 2 control signals, one is write, another is read. So if we read, let's say first write the data. So write means write signal should be enabled. And in the vertical line, you give the analog sample data. Then since the NMOS transistor, the data from source, it will go to the drain or vice versa, and capacitor will be charged. Okay. So that means data is stored. And if we want to read that data, make read signal enable. Once the read signal is enabled, then upper transistors will be enabled. And similarly, the lower transistor is, because already it is charge is stored. So this data will go to the horizontal line. You can read that. So this is the basic fundamental mechanism of analog storage device. Okay. Now, up to this point, is there any question? Please, because then only I'll go to the next sections.
Sir, I have questions, sir. Sir, please figure, sir. Can I see the figure, sir?
Yes.
Sir, in this figure, suppose the value is 4.5.
Value of what? Where?
So whatever I want to write,
No, 4.5 is what is the unit?
The voltage.
Okay, fine.
Okay. So voltage, I'm enabling the write. Then the NMOS source is positive, and that near about 5 volt, it will come across the capacitor.
Yeah.
And capacitor will store charge.
Okay.
Then, sir, when I'm reading, enabling read, then that transistor is switched on, and as the positive charge across the gate, so that downward transistor also switched on. Now the source of that transistor is connected to ground, so ground potential will come across the end point, that means the vertical line, isn't it, sir? Horizontal line, sorry.
Okay. Okay, you can think in that way. Fine. Then all that you can do is this right read bar, you can do that. Okay. In the right line signal, for example, let's consider this is you are reading the data. Then if you consider that instead of writing, if you say it's reading, then
okay.
So we can say read write bar.
Okay. Yes, sir. Yes.
Then it is all right.
Okay.
Okay. Just a little bit of change you can do that. Write read bar. Write read bar. What I'm saying that when you are going to read the data, okay. Normally, or read write bar you can say. When read means 1. So when you are giving 1, what will happen?
This transistor will be switched on.
These transistors will be switched on, and whatever the data is here, that will be that you can read. Okay.
Yes. Yes, sir. Yes, sir.
And if you want to write the data, then again by switching on the same transistor, this data you can store it.
Yes, sir. Yes, sir. Yes, sir.
So that can be done.
Yes. Yes, sir. Okay, sir. Thank you, sir.
in fact, I think read bar somehow it has been missed. Okay, you consider these
Okay,
things.
sir.
Okay, right, read bar. I will come to that in details also. So you understand
Okay.
how you are storing the data. So how you are storing the data? First, the analog data will be sampled, and this sample data that will be stored in the memory, right? And these are the basic memory cell. Yes. Any questions, Mihir?
No, sir. Thank you,
Okay.
sir.
Now we'll consider floating gate transistors. Okay. So unless we understand the principle of floating gate transistors, it will be difficult to explain these analog memory concepts. Okay. So first we have discussed by and large the fundamental principles of analog memory, where the data will be stored in the capacitor. And by switching these transistors, we'll take the data or we'll write the data onto the capacitor. That is the basic principles. Now we'll see how the floating gates are employed for storing the data for a long time. Now, what is a floating gate? A floating gate transistor is a complementary metal oxide semiconductor. Okay, I can skip that. Please first let me know, uh, because last year I explained floating gate transistor for VLSI students. Should I need to repeat those things or I can skip? Hmm? Hello, nobody's saying anything.
Sir, can you
Sir, a
just
revision would be
go through
sir, revision would
a
be
short
a good thing,
revision?
sir.
Mhm. So, okay, Meet, should I go through this floating gate transistors?
Yes, sir. Yes, sir. Yes, sir. Yes, sir. That will be good, sir.
Okay. A floating gate transistor is a complementary metal oxide semiconductor technology capable of holding electrical charges in a memory device that is used to store data. Okay. Now, floating gate transistors were first used in erasable programmable read-only memory, EPROM and then square PROM. So these are widely used for flash memory also. Okay. Now, flash memory is what? Is a type of square PROM that is programmed and erased in large blocks. The flash chips are basically this erasable programmable read-only memory. So these days they are very, very popular, and they are based on the floating gate transistors. So each transistor has two gates. One is the control gate, another is the floating gate. We will discuss these things in details. Now, this square PROM, EPROM, these all are digital memory, digital non-volatile memory, which are used for storing the data permanently. And all of we are quite used to this flash memory, which are basically square PROM or EPROM. But then how these will be employed for designing analog memory, that's quite interesting. First, let's have a review of the floating gate flash memory shell. Normally, in fact, single gate NMOS transistors, we all know that these are drain, gate, and source. This is a structure. Okay. And the silicon dioxide, then polysilicon, and gate. And this is a P-type substrate. Whereas in the floating gate flash memory, there are control gate, floating gate, and this is oxide, gate oxides, and this tunnel oxides. And here source and drain. And in between there will be a channel. This is substrate. So we all understand the concept of NMOS transistors, and here only what is the difference? A floating gate has been introduced here. This is an additional gate. What is the purpose of the floating gate? Now looking at that diagram, the students can at a glance can tell what is the purpose of the floating gate. I've already told the answer. These are used for flash memory where information can be stored permanently. Then what is the purpose of the floating gate? What is the dielectric between floating gate and control gate?
Sir, oxides, gate oxide.
Gate oxides. That means if somehow the charge can be trapped onto this gate oxide, that means in between two control gates, then unless we disturb it, that charge will be trapped over there, isn't it? Because this is not directly connected
Yes,
to source or drain or anything. So somehow if you can put charges over here, in between two gates, floating gates and control gates, that charge will be trapped and it will be untouched unless you do some kind of, you give some external force from outside to bring those charges. So that's the fundamental concepts. You do one thing, since you are doing MTech and many of you might be going for research, whenever there is any purpose, first you must have to understand what is the key point, what is the salient feature of that, and how that can be overcome. Now here, as I told you, our target is to design a memory where data should be stored permanently. That means non-volatile. What is the meaning of non-volatile? Even if the power goes, still information should be intact. Now here information, in which form the information can be stored? Here only the charge.
Sir, charge.
Exactly. So this charge should not be disturbed, It should not go away. That means if somehow it can be trapped, and this is possible if in between two control gates there is a dielectric and where charge can be stored. That's why this floating gate has been brought in. Now how it works. Now basically flash memory works by charging or discharging electrons to and from the floating gate. That we understand. If we say that charging means 1, then discharging means 0 or vice versa in negative logic. So a bit 0 or 1 state depends on whether or not the floating gate is charged or uncharged. If we say that charge in floating gate, the charge is there, it is a 0 state, then vice versa will be 1. Or in the reverse logic also you can think that if it is charge is 1, no charge means 0. So when electrons are present on the floating gate, current cannot flow to the transistors because it will give the force in the opposite directions. So the bit state is 0. And the reverse can take. So when the electrons are removed from the floating gate, the current is allowed to flow and the bit state is 1. So that means depending on the condition of the floating gate, whether there is charge or not, we can consider a state 0 or 1. So these are in fact the MOS transistors. I'm giving this diagram once again to review the concept of fundamental concepts of MOS transistors. So these three things are very important. When, let's say, in the gate, the VG, the gate voltage is below 0, then what will happen? This is the diagram you can understand. Negative gate voltage below 0 means less than 0 means negative voltage. And this should be the positively charged particles will be very near to that. If we give more but still less than threshold voltage, is greater than 0 but less than threshold, then what will happen? Some repulsion will be there, some depletion layer will be formed. And when it is more than threshold voltage, then yes, the current will be flowing. This is the inverse region and this is the depletion region. So this is the basic concepts, we all know that. But what is the principle of operation of E-square PROM using floating gate MOS transistors? Why I'm saying the E-square PROM concepts? because if we understand EEPROM concepts, then we'll understand the concepts of analog memory as well. So floating gate MOS transistors are widely used as a digital world as EEPROM. I'm telling you, the students, for interview questions, it's a very important questions, but it's the basic components of EEPROM or EEPROMs. These are floating gate transistors. So how is floating gate transistor in EEPROM? How to program? How will we programming? To program the device, a high voltage, say 16 voltage for instance, is applied. But these days today, the high voltage is not 16 volt. Even the normal voltage, the supply voltage, using that we can program it. You must have noticed that your pen drive, when you insert in the USB port, the pen drive is programmed using the normal voltage. Because now the voltage level has come down to 1.1 volt. So even if you give 5 volt, that's enough. So when a high voltage is applied between the drain and source, this causes electron to avalanche to the source towards the drain. Is okay? So as the SiO2 layer is very thin. Once again, I'm showing the diagram. Just have a look at it. So this SiO2 layer, okay, oxide layer, is very, very thin. So what can happen? If the layer is thin, then what will happen? Electrons travels from the source through SiO2 layer to the floating gate, where they are trapped between the oxide insulation layers. This gives the floating gate electrode an electrical charge. Okay. So hence the threshold voltage of the floating gate is increased. That means what happens? When the electrons are trapped over there, then you have to apply more voltage in VG to make the channels between source and drain. So the formula is the threshold voltage of the floating gate transistor is increased. Change of VT, that is del VT, is also given by del VT equal to del of QFG by CFG. Del of QFG is what? The charge, the change in the charge in the floating gate divided by the capacitance in between. Because there are two plates, we can assume that with the dielectric oxide. So there is a capacitance. So the charge, so your threshold voltage is getting also increased. That means the diagram will be like that. So earlier, what was the threshold? Now the threshold has been increased. That is the characteristics curve. That means somehow we can say that is a kind of reconfigurable transistor. By charging it, you are configuring it to a different VT. Okay, your threshold voltage has been increased. Now, as long as you are not disturbing it, this charge will be trapped over there. So that doesn't depend on whether there is any voltage source in VD or VS or not. It doesn't matter. Charge will be there. And depending on the charge, then for a given voltage, gate voltage, current will be passing through it or not. So in that way, you can make the mechanism of 0 and 1, which is stored. So in nutshell, we can say that if charge is stored, if charge is trapped between control gate and floating gate, if I say this is 0, then if there is no charge, that will be 1 or vice versa. So this is the basic mechanisms of the non-volatile memory or floating gate, which is based on the floating gate memory. So any question? Yes, Mihir?
No, sir.
Is so is okay with us?
Yes, sir.
Okay. So this when the floating gate transistor is bathed, now how to remove the charge from there if we want to erase it? That's simple. When the floating gate transistor is bathed to ultraviolet light for some time, the charge on the floating gate will disappear because the ultraviolet light, it will have the photon particles, it will give the energy, and it will the charges will disappear from there. So the mechanism for discharge is just give ultraviolet light. That was earlier erasing for this. So because of the very good insulation properties of SiO2, the charge on the floating gate leaks away very slowly. That's why I told you that it will be stored for a long time, and VT will keep high for a long time. Because what you have done, essentially, you have shifted VT. The threshold voltage has been increased, and that is the reason it will be stored for a long time. So a strong negative charge on the control gate forces electrons through the tunnel oxide layer into the channel. So these days, what happens, earlier, when we used to use the erasable programmable read-only memory or programmable read-only memory for erasing the data from the memory, we had to take it out from the circuit and we had to keep it under ultraviolet lamp for quite some time to erase it. That's a time-consuming matter. But now, in fact, within the circuit, you can do. Definitely, when you use these, the memories, the flash memories, definitely you don't bring them and put it under ultraviolet ray. On the circuit, it could be done. So what you have to do? Strong negative charge on the control gate forces the electrons through the tunnel oxides. So by applying higher voltage also, negative, you can discharge them. So that is the concept. For analog circuits, there are some applications of programming property of floating gate MOS transistors such as neural network. So since charge, these concepts, storing the charge or discharging the charge, give the concept of analog memory. So this is a floating gate device. When the floating gate device operates, there is a transfer of electrons from the drain to the floating gate or floating gate to drain between the tunnel oxide layers. So these are charging and discharging properties of the floating gate. So that already we have discussed. Now we will understand how these concepts can be exploited in designing analog circuits. So to understand the concepts of design concept of analog memory, first we have to understand the design concepts of digital memory. Even though you know this architecture of digital memory, I'm just reviewing it at a glance. Digital memory, typically you consider random access memory. So there are address lines and data lines. Typically we call address bus and data bus. And control signals are like a read-write bar. If you see here, is it readable? Hmm?
Yes, sir.
On signal, it should be read-write bar, mind that, Okay, if it is read, then it's not write. And when it's write, it's not read. So let's say if we consider 1 for read, then if we give a signal
0 for right.
0 for write. But this concept, there is a drawback in this concept. This is the concept given by Motorola and some almost 50 years back in early 70s. Motorola concept, and that time in fact, the competition among the vendors was how to reduce the number of pins. That is valid still as on date because the cost of the semiconductor devices depend on the number of pins. So read-write bar, we all know that at a time, we are not doing read and write both the functions. Either read will be performed or write will be performed. That means either the data will be written onto the memory or data will be read from the memory. Since at a time we will do only one work, then same control signal can be utilized for read and write both. Like if I say that 1 for read, then 0 for write. So when we'll be giving one signal over there, it will be for read, and when we'll keep signal 0, it will be for write. Fine. You have reduced the number of pin by 1, but the drawback is always it will be in one of the modes, either in read mode or write mode. But if you don't want anything, neither read nor write, then that cannot be done. So in that case, you will be requiring two signals. One is read bar, another is write bar. Now read bar, write bar, we all use this bar complemented signal because we are dealing with the metal oxide, like complementary metal oxide semiconductor. Everything is in terms of complemented form. Okay, but why these two? The advantage is if you don't want read or write anything, then it will be that state is also possible. Now why that state is important from the power dissipation point of view? Because when the circuit is in one of these modes, read or write, then some amount of power consumption will be there always. And now, in fact, we are designing, whenever we design a chip, one of the major constraint is how to reduce the consumption of power. So there is a trade-off. One number of pin is getting increased, but at the same time, you are reducing huge amount of power also. Because there is not a single cell. As the memory size is getting increased, more and more number of transistors are there. Like 1 megabytes of data. How many transistors you calculate? So that's the thing. This concept was derived by Intel. So for all the Intel chips, you will find read bar, write bar, both are there. And now Motorola is also switching over to this Intel concepts. In many of the Motorola chips, you will find read bar, write bar, both are there. Okay. So here, if you consider this is upper diagram is the block diagram of the memory in general: address bus, data bus, and control bus. And control signals consist of, one is the enable or chip select, another is the read bar and write bar. And data bus is bidirectional because data can go in or data can be read out. And address lines are single dimensional, unidirectional. Okay. Now if we expand this, each location consists of a number of cells. So a number of cells will be there. And how? Address lines will be there. So there must be an address decoder which will select one of the rows. So a number of rows will be there, a number of columns will be there. Okay. At a time, only one row of a particular column will be selected, not all the rows. And which row will be selected? That will be governed by the address signals. That's all. So here in this diagram, input line and output lines are separate. But now, in fact, to reduce the number of pins, input and outputs are the same lines. Because at a given time, either input operation means the write operation is performed, or output operation means read operation is performed. So this is some of the chips, they have some 2 chip select line, but these days only 1 chip select line is sufficient. Read, write, but there will be read bar, write bar, address line, and this is the data bus. This is the block diagram. So since it is 128 into 8, that means each row will consist of 8 bits. So 8 flip-flops will be there in to store each bit. 128 means 2 to the power 7. So 7-bit address lines will be there. So 80 to 86. So this is the basic memory cell. Right line, this. So here, fundamental thing is two NOT gate connected back to back. That forms a transistor. That forms a memory cell. How? You forget about all other transistors. You concentrate only these two NOT gate. Say, somehow the input of the upper NOT gate is 1. So output will be 0. That 0 comes to the input of the second one. That will be 1. So 1 will be latched. Continuously, you just say 1, 0, 0, 1. So 1 will be permanently stored. Now, if you want to change 1 to 0, then let's say give 0 to the input of the upper NOT gate. That will become output will be 1. That 1 comes here and 0. So 0 will be latched. So this is the storing mechanisms, and this is called flip-flop. Now here how we have used two transistors. So your M5 and let's say M0. These are transistors. Let's say right hand side transistors. Okay. In the BL line, if we give 1 and M6 transistor is made on, then what will happen? Let's say BL line is 1 and M6 transistor is switched on. What will happen?
Sir, one will be latched.
So this one will come to Q. Okay.
Yes, sir.
So this one output will become 0 to 1. So 1 will be latched. Simple. Okay. That's why BL is called the bit line. And BL in the left hand side is BL bar. Is a complement of this. In many flip-flops you will find, okay, you will find one is Q, another is Q bar. Here also is the same thing. Okay. And can you tell if you want to read data, how to read? How would you read the data?
Sir, BL bar is 0.
BL bar, in fact, BL bar is not the control signals. Read or write will come from the control. What is the control line?
Sir,
Yes, sir.
WL.
There's a word line. Word line. Sorry. Yes,
Yeah,
sir.
normally
Word
what
line.
happens, I'm telling you, in a practical design, what we do, because this is one line, BL line is the writing the data. Okay. If we have a separate line, let's say for read, we can have another line. You can use the transistor. And those transistors, what you can do, we can control by separate read signal, and the data can be read out, which has not been shown here. Here only for data writing that has been shown. Understand?
Yes, sir.
Yes, sir.
So these are basic cell. These are concepts. Two transistors connected back to back. That forms a basic storing element. And these all are internal structure of the memory. This is the memory cell.
Sir, can you
Yes.
please repeat how to read the data from the memory cell once again?
Okay. Now, let's say write we have discussed. We have two other lines. let's say 2 other vertical lines in the same way. Like this is the write line, we have the read line, RL. We can have that.
Yes, sir.
And then,
Yes, sir.
and there will be 2 transistors. One is for Q, another for Q bar. Let's consider the lower NOT gate. From that, you extend this line vertical and connect it to the transistors. Okay, source line. And this transistor, let's say, you consider it M4. At the gate, if you give 1, then what will happen? Whatever the data that will be going to the output sides, is it not?
Yes, sir. Yes, sir.
And that is the read operation. So write data, that is one line, and read data, that is another line. Why you are not giving any response?
Sir,
Yes, sir.
but
Understood, sir.
from Q, suppose if 1 is latched, then from Q we will get 1, but from the another side of the lower NOT gate, we will have the complementary value of that
That is 0.
previous value.
You can get 0. Okay.
So how to recognize what is the
This
actual?
we'll get it 1. We'll say it is 1. We'll get it 0. Normally for the memory, we don't deal with both the outputs. Okay. For flip flops, we have Q and Q bar, but we use only one line. Okay. You forget about Q bar.
Okay. Yes.
We will simply
That
take
means
the
we have to put both the word line and the read line on the same
exactly,
side of the latch.
exactly,
Okay.
in
Yes.
the same
Yes.
way.
Okay. Thank you.
Now what we can do, we can replace this NOT gate by these transistors, because here we are using CMOS. In CMOS NOT gate, how many transistors
Yes,
are
sir.
used? How many
2,
transistors?
sir.
2 transistors. So
2.
for both of them, 2 and 2, 4 transistors will be used. Listen, output of one transistor will be connected to the input of one. Output of one NOT gate will be connected to the input of another NOT gate, and vice versa. So this is the concepts of the memory cell. Okay. So this is the basic memory cell. And here we can use normal design is very simple. We have a decoder. This is a basic memory cell where all these elements will be stored, and input line, output lines. Now this decoder, again we can divide. For example, let's say we have 16-bit address lines. 16-bit address lines means 64K of lines, and decoder will also be very complex. So you can divide 16-bit 8 into 8-bit. So row decoder, column decoder, then select one of them. So in that way, your decoding is done. And output and input, to bring them into same line, what you do, you use the tri-state buffer. Tri-state buffer in the input side and tri-state buffer in the output sides, and then connect input and output. Because at a time, either you will be selecting the input or you will be selecting the outputs. So through the same lines, you can get input or you can get output, which is known as the bidirectional lines. That is the mechanism of designing SRAM. So SRAM design is simple. If you write the code, so what are the basic elements here? First, you design the basic cell. You store them as a function, and you can utilize them again and again for doing it. So these are pin configurations. So here's the row column, as I told you. So these are the basic fundamental concepts. Now here, let's say I'm giving you a task for designing the analog memory. So this is the basic concepts. Okay. Forget about the how read or write lines will be connecting. Basically, we are using 3 transistors. For here we have 2 lines, one for reading lines, another for writing lines. And they will be, this is the basic cell. So just like your digital memory, This analog cell will be, these will be like that. This is the input and these are the outputs. And here a decoder would be there, which will decode. And each rectangle, small rectangle, within the rectangle, what will be there? Within the rectangle, this analog circuitry will be there. Okay. Capacitors and 3 transistors will be there. And these transistors, instead of that, we can use floating gate transistors. No problem. And connect them in that way. So this is, you tell me, this analog memory, it belongs to what? Is analog, digital, or mixed signal? What kind of circuit it is? Analog or digital or mixed signal?
Analog.
Hmm?
Or it may be used as a digital also.
My question is straightaway, is it analog or digital or mixed signal? What kind of circuit it is?
So mixed signal.
Why?
So because the memory digital in nature.
Good. That's is a mixed signal circuit. Because decoder is digital and control signals which will allow a particular thing to do. So there also some logic will be used, isn't? So it's a
Yes,
mixed
sir.
signal. So these cells are analog and these decoders and all, these are digital. So it is a perfect, is an ideal example of mixed signal circuits. That is the analog memory. So in analog memory, before that, the signal inputs, the signals will be coming from where? Do you need
The
so many
processor.
columns like digital? Tell me, for digital, do you require so many columns? Why so many columns are required for digital? These columns indicate what?
Each bit.
So one
Bit.
bit.
Is there any concept of bit in analog?
No.
So, do you require so many vertical lines?
No, a
Not
single line can store the
Yeah, also
value.
here, this line, let's say this y-axis, okay, this 0, 1, 2, these are n. N means sample numbers. These are value, analog value. That is going to be stored in the capacitor. There is no concept of bit. So if that is the case, then do you require so many vertical lines?
No, sir.
No, sir.
Only one vertical line, and each block, okay, the small element, what I'm saying, basic memory cell. What is a cell? The cell consists of this, these transistors. That's all. Where data will be stored. That means what essentially we are doing, input signal, after input signal, what we require? Input signal is the analog signal. So many vertical lines are not required. Only one vertical line is enough. But before that vertical line, you should have a sampler. A sampler is what? What is a sampler?
Sample and hold circuit.
What is that? It's switch basically. It's
Yes, sir.
nothing but
Yes,
switch.
sir. Yes, sir.
Here you don't require sample and hold circuit. Sample is enough because holding is being done in the capacitor. So you don't require separate holding circuit. Listen,
Okay, sir.
Yes, sir.
because here what is happening? Where the data is held? Data is stored in the capacitor.
Capacitor.
So here it is coming through this vertical line. the right line is enabled, so data will be entered and the capacitor will be charged. That's all. So a switch will be there. So analog signals, after that a switch will be there. You switch on this and that data will be coming. That means the discrete analog signal which will be stored in the capacitor. Okay. Up to that, whether there is any questions or not, please.
So in this case, what is the address line and what is the data line for analog memory?
Fine. I've already discussed that. Again, once again, I'm telling. Let's consider this is your analog memory circuit. This is a SRAM. You forget it is SRAM. So address lines will be there. A decoder will be there, which will decode a particular row. Okay. In each row, there will be only one column. Forget about the rest of the columns. So you consider only the first column. So depending on that, a switch will be there.
Yes, sir.
So that will be enabled. If it is enabled in that row, the data will be written. It's like that.
Okay. So actually, sir, the write and read, these two are actually controlled by the address line.
No, separate. That will be ended with the address lines. Write and that row. Okay, that will enable this to be stored. Okay, not only write. For an example,
Only write. Yes. Actually,
here
address line should be there.
Yeah, address one address line.
Yes, sir.
On row will be selected along with
And
that
write WR bar.
WR bar and enable also, which is called chip select. That
Chip
also
select,
has to be
yes.
selected. If chip select is not there, even though you give address, you give write, nothing will happen.
Yes, sir.
So that's why some digital circuits will be required, which will select a
Yes, sir.
particular row. So most of the things are just like digital. Only the storage element is different, where data will be stored in the capacitor. That's all.
Yes, sir.
So here the thing is that you tell me this storage concept is continuous analog or discrete analog?
Sir, it is discrete analog.
analog, sir.
It is discrete analog, because continuous analog you cannot store like that here using the switching transistor. And moreover, if you can do, let's say for 20 milliseconds or 10 milliseconds, then huge capacitors will be required, which will be beyond the limit of the VLSI technology, isn't it?
Yes, sir.
So this is now here. There's a small limitations. Some leakage will be there. If there's a leakage, why leakage? Can you tell me? You have stored and all these things. Logically, it sounds very nice, but still there could be small amount of leakage from the capacitor.
So that is the property of capacitor.
No, property of the capacitor is not the leakage. Anybody?
Sir, through the transistor, while the transistor is still some kind of on, through the transistor, the capacitor can be discharged for a small amount.
Yeah. Through the transistor, there will be leakage. The reason being, if you just make the equivalent circuit of the transistor, you all are familiar with the hybrid parameters. Equivalent, some resistance will be there. And
Yes,
if you
sir.
make equivalent circuit, is kind of RC circuits will be there, and there will be leakage current. So this leakage current, if we can make some mechanisms, whatever the current is being, the charge is being leaked, that amount of charge will be replaced here. Then there is no problem.
So refreshing is required.
Yes, sir.
No, refreshing for dynamic memory, we do refreshing, but here what we will do? That means we need some control mechanisms Now let's come to little bit of control systems. In control systems, let's say we all use the voltage stabilizer. Okay, for freeze or anything, we use the voltage stabilizer. What is the purpose of the voltage stabilizer? It stabilizes the voltage. That means if there is a fluctuation of the input voltage, still output will be constant. That is the purpose. Okay.
Yes,
Yes,
sir.
sir.
Now, say you consider a transistor. Very simple, let's say primitive transistors, NPN. I believe you are familiar with this bipolar junction transistor, BJT. Or even you can consider MOS transistors. Now, if there is a drift in temperature, then what happens? For BJT, the collector current will be changed, because if there is a change in IB, there will be change in IC, because IC equal to beta IB. Then what you do for thermal stabilizations, we use a feedback resistors by connecting a resistor from emitter to ground. Okay, this is called a feedback resistors, and this is for temperature stabilizations. Same thing. This is basically doing what? It is making a feedback. For example, feedback amplifier. Why you use feedback amplifier? Because the
To
stability of
minus
the,
the error, sir.
yes, for stability of the gain. Here also, that means we have to use a feedback circuit to get it stable. Because feedback is used for what? You know, AFB.
Calculating the error.
Yeah,
So
AFB
minimizing the error, sir.
for an amplifier, feedback amplifier. If AFB is the gain in the feedback, AFB equal to A by 1 plus A beta, where A is the open loop gain, A by 1 plus A beta. Beta is the feedback loop. That means by doing a feedback, you can make a system stabilized. That is the basic fundamental principle of the control systems. So here also you can do the same thing. What we are doing, we can use an operational amplifier, and the output, this input, this is being feedback over here, where it is connected, is given to the floating gate. That means the charge, what is being leaked, that is being stored here, and that will be finally stored into the capacitor. Or alternately, another circuit can be done. This capacitor input, that by giving to the input of this feedback amplifier, this is a feedback amplifier connecting, you can, the leakage current can be maintained. Anyway, this is the basic principle, where in the capacitor the charge is stored, and these are some transistors. So that is the DRAM cell. This is a analog memory cell, which are, the type is just like DRAM style. So this is the basic memory design. Now, if there is any questions, please. So is there any questions from your sides?
No,
Mihir? Please ask me if you have any questions or anything regarding this, the basic concepts of analog memory and design of analog memory. If you don't have any questions, then I will ask you some questions. Tell me here, where the floating gate transistors will come in the picture. I've been
Sir,
discussing about,
in place of the capacitor,
yes,
we can use the floating gate transistor to
okay, fine,
reserve to store the charge.
okay. And input signals will be, in fact, when that will be the analog signal, isn't it?
Yes,
Yes,
sir.
sir.
Okay. And that will be stored here. And if we want to reduce this, if we want to discharge it, apply high voltage, and this will be in the negative directions. This will be discharged. So the concept of memory, please, if there is any questions, you make it clear. Yes, we will go to the next sections then. Sure. Do we have some time? Hello?
Yes, sir.
Yes, sir.
Yeah. Yes, Mihir, please, if you have any question, please. Mihir, is he here or his connectivity is lost? Yeah. So can I go to the next section?
Yes, sir.
Yes, sir.
Now we'll go again to the digital sections. You know that we started discussing about FPGA, but not in that details. So today we'll discuss about FPGA in more details. So FPGA, as we know, that consists of three basic building blocks: CLB, IOB, and switches. Switches are made using the multiplexers, which are known as,
Sir,
yes.
sir, some problem was there. Sir, you was calling me.
Oh, some, yeah, that's what I was feeling, that you had some problems with the network, isn't it?
Yes, sir.
No, I was asking if you have any questions on, have you been
No,
able
no,
to
sir.
hear what
Yes,
I
sir.
was talking about?
Yes, sir. Yes, sir.
Okay. So these are the basic building blocks, the CLB, IOBs, and switches. And the basic advantage of FPGAs are they are flexible and they could be used as a reconfigurable devices. So reconfigurable in the sense they can be configured to any hardware circuits. So let's say you have designed a hardware and later on, if you want to change that hardware, just by changing the program, you can change the whole thing. So your risk factor is very less. That is the most important feature of FPGA. For example, if you design an ASIC and after designing, if you find that it needs to be altered because certain features are missing over here. And these days it is very important, especially when there are a lot of players, means a lot of competitors in the market. If a particular vendor offers some features, especially for the consumer product, then definitely you have to provide that. Otherwise, it won't be sold in the market. From that point of view, these programmable devices are very important. And that is the reason FPGAs are very important, because they are reconfigurable devices. But still, as on date, for consumer products, FPGAs are not popular because of their price. They are much more expensive compared to DSP processors or microcontrollers as on date. Attempts are being made to reduce the cost of FPGAs. FPGAs with better features and all are coming, but still the prices are not stable. So obvious question is then why? What for FPGAs will be used? What are the applications then if it is so expensive? FPGAs are used for high-end applications still as on date. What are high-end applications? High-end applications like air traffic control. In aeroplane, there are various control circuitries. Their FPGAs are used. Okay. Or software-defined radio, which is quite expensive, which are not used for consumer product like your mobile handsets and all. In mobile handsets, definitely FPGAs are not used because their cost is higher. I remembered one thing, almost a decade back. One professor of Jadavpur University, he was doing research. So one of his students was doing work on FPGA. In fact, I delivered a talk over there on FPGA, and they were quite inspired and started working on FPGA. And one paper they wrote, and he showed me the paper to give my comments on the paper. The paper was speed control of a DC motor, and FPGA was used. So when I saw the paper, I told the professor, look, this paper will be immediately rejected if you give it to any good journal. He asked me why. I said, I'm telling you from my industrial experience that nobody will be using speed control of a DC motor, FPGA, for controlling that. The reason being, the control, a DC motor, the frequency is what? We are basically taking the power of 50 hertz, which is a very, very low frequency. And from that, we are controlling the power and controlling the armature voltage. And armature voltage will be controlled by using the thyristor devices. And in the thyristor, if you give the gate signal, okay, the control gate signal, you can change the RMS of the full wave rectifications, and that control will be done. I said that an FPGA, the FPGA which was used that time, it was costing about almost $100, and which could be done by a microcontroller of $2. And if we use this thing, we will buy this product. So this is very important. And when I explained that, he understood. And that means from here, what is the lesson? FPGA has come in the market. That doesn't mean that for every purpose we have to use FPGA. FPGA still, as on date, it is not widely used, or it's not wise to use for consumer applications. It is used for very high-end applications, where cost is not that much of a factor. Okay. For an example, if the cost of a product is something like, let's say, $5,000, then saving $20 is not a factor. But if the cost of a product is few dollars, then few cents makes a lot of a difference. So from the engineering point of view, the cost is a very important factor. So we should be careful about using any kind of chip. So first, our selection should be what is the cost. what is the flexibility, what is the power dissipation, what is the robustness. So from that point of view, FPGA offers a very high speed, but of course that speed is less than ASIC. Why? Obvious question. The answer is ASIC doesn't require any switching circuits because ASIC has been designed for a particular applications. There is no flexibility, but FPGA has been designed keeping wide range of applications in view, wide range of high-end applications. So to provide that thing, that support, we require these switches. And as the complexity of the circuit increases, the complexity of this router will also be increased. Power dissipation will also be more. And to reduce that power dissipation to a certain extent, some intelligent power dissipation circuit has to be given. So that is an additional circuit. So that's why this cost of the FPGAs are much more than ASIC. But ASIC doesn't offer the flexibility. Okay. So this point has to be made very clear. So okay, still we have some time. Now here, typical the structure of Xilinx, the Vertex FPGA, Vertex initial stage. Vertex is very powerful, but now various types of FPGAs have come in the market. So basic structure of the CLB consists of a number of slices. Now here, look, this architecture you don't have to mark because now there are different types of architecture. Okay, internal architecture for a particular FPGA is not that important unless you go for designing an FPGA, or you can go for making a VLSI chip. So there are two aspects. One is you are using FPGA for your applications. So basically you are an application engineer where FPGA is used as a building block. Another area is, as a VLSI design engineer, you are trying to design FPGA. Now, if you want to design FPGA, then I would suggest you do one thing, you think in that way. You don't have to go for a particular design, but for your reference, you can go for Xilinx or Altera, Actel, this kind of FPGA. So here, fundamental thing is first some CLB, because whenever we'll be designing, our concepts should be system concepts and top-down approach. So our fundamental building blocks will be CLB, IOB, and router. So if we can write the code for each of them, only one, then utilizing them, connecting in proper fashion, we can make, depending on the complexity of this. Now, how CLB to be designed? Now, first state we go to the basic building blocks, very fundamental things of CLBs. What is there within the CLB? CLBs are basically designed from the lookup tables. What is the lookup table? Now, when we are making the programmable logic functions, that means the logic circuit should be altered. Now, within the chip, definitely this AND gate or gate, that you cannot change. Or if you want to do that, then large amount of switches will be required. You will be requiring very large number of AND gates, like NAND gate, NOR gates, and lot of switches, and very, very complex switches. So this is, instead of doing that, you think in that way, designing logic circuit in an alternate way. That is the lookup table. Now, how lookup table can be implemented using the memory devices? Now, what is the fundamental concept of the memory devices? Memory consists of a number of rows, what we call locations, and in each locations, number of bits can be stored. Now, let's say we want to design 16 into 1 bit memory. 16 into 1 bit memory means there are 16 rows and there will be 1 bit in each row. So for 16 bit, how many address lines will be required?
4, sir.
4 bit address lines will be required. So let's say A, B, C, D are the address lines and Z is the bit. 1 bit will be stored. So here, in fact, this is the truth table. Whenever we design any logic circuit, it will have a truth table. Okay. So truth like here 0, 0, 0, 0, 0, whatever it is. So we can store this entire truth table can be stored in the memory. Now let's say this memory is SRAM. Okay. Or let's say this memory is E square PROM. So you can store it. So any logic circuit, any digital circuit consists of a number of logic circuits. Okay. So these logic circuits, how they are, like output of one gate is connected to the input of another gate in that way. So it is basically a network of logic blocks. So this network of logic blocks can be implemented by this memory, a number of memory chips or memory units, and these memory units will be interconnected. So that means if we have a number of CLB or number of LUTs, lookup tables, and some switches, so just by connecting these switches and lookup tables, we can make the desired logic circuit. So within FPGA, it's like that. A large number of lookup tables are there. They are placed in row and column fashion, and there are a number of switches, and these switches, just by they are interconnected, and by changing the connectivity, we can make the different kind of functions. So that is the fundamental concepts of your FPGA. Okay, like here, let's say this is a circuit, typical logic function. So these things, the functioning of this is placed onto the lookup table. So when you write a code in high level language, what happens? These codes are transformed into a number of CLB. So the contents of CLB has to be defined for making a particular functions, and how these CLBs will be interconnected. So there are two types of information. So total bit stream consists of one part is the contents of the lookup tables, and second thing is the control signals required for routing. Okay, so these things together forms the total bit stream. So when you write in high level, the CLB will have its contents which will be defined. Okay, so for all the CLBs, this what should be the contents that will be defined, and how these CLBs will be interconnected. Then it comes the functioning of these switches. The control signals for switches will be given. So that is the total execution of your FPGA. Now here FPGA is not working like your normal CPU, where step by step in a sequential fashion the execution is going on. Here, so what you can do, let's say in a complex functioning, when you are dividing into many logic blocks and all, many of them can work in concurrent, in parallel. Okay, so it's basically hardware implementation. You are programming it, it's true, but this programming is basically the hardware programming. So the concepts of programming a von Neumann computer and concept of programming an FPGA is totally different. Okay, so it is reconfigurable in the sense by changing these things by programming you can change it. But now another type of FPGAs have been emerged in the market that is called dynamically reconfigurable FPGA or on the fly reconfigurable FPGA. What is the meaning of that? On the fly in the sense like, let's say FPGA, within FPGA all the parts, like let's say there are 4 portions A, B, C, D. When A, B, let's say static, and D is getting changed. Okay, now it is D, after that it will be something. So when it is working, during that time, some bit stream can be downstream or can be downloaded to make the required change. This is called on the fly reconfiguration. So some part is still working, but some part is getting configured. So these are very, very important for many high-end applications. You must have noticed that in a normal CPU, the operating system, what it does, some part of the operating function systems, they are loaded. Okay, but some part, whenever it is required, sometime they are brought in and downloaded. Similarly, for FPGAs also, the functioning of the total FPGAs, some part is functioning and some part is getting changed to make the overall functioning dynamically change. Now this is RTX 7 FPGA. That is also latest state-of-the-art FPGAs. So within this FPGA block, apart from this basic building block like CLB, input-output blocks, switches, there are also some RAM, DSP blocks, and global routing network. Now why RAM? RAMs are very much important, large amount of RAM for image processing applications. Because for image processing applications, the image frames, they need huge data to be stored. For example, let's say if we need 25 frames per second, and each frame consists of, let's say, 840 into 1024. So that means 1024 into 840 into 50 into 24, because each pixel consists of 24 bits per second. It's a huge amount of data. They need to be processed. This is for video applications. So that's why RAMs are also there. These are data RAM. Some DSP blocks are there for image processing or signal processing applications. Huge amount of computations have to be done, and most of these computations are multiply and accumulate. Then real imaginary computations, square root computations. So for that, some DSP blocks, building blocks are there, and global routing, clock. This global routing network is very strong. Routing network is there. Okay. So that's all for now. Up to that, if you have any questions, please. Do you have any questions on FPGA?
Sir, I have a question.
Yes.
Sir, you have said that if we have four blocks A, B, C, D like that, so A, B are fixed and C, D can be changed according to the dynamically actually.
Hmm.
So where from the new bit stream will be generated and downloaded?
That will be control, some computer will be there with that. When
Okay,
it's
okay. Some processor is required, right?
some processor will be there which will be doing this downloading.
Okay, okay.
Okay. Normally, FPGA alone uh, doesn't do the job. If you see the real circuit for FPGA, along with FPGA, at the top of FPGA, there is a control unit, which is a processor, which does all these things. The bit stream initially what happens when you power on, then there is a EEPROM, square PROM. In the square
Yes, sir.
PROM, these bit streams are stored for a particular circuit. Okay. So
Okay, sir.
the control unit, it gives command to a control unit, which is basically based on some CPLD based controller circuit. It gives a command to the controller, and controller gives the necessary signal to this square PROM such that the bit streams will be downloaded from square PROM to FPGA. Then
FPGA.
FPGA, once the bit streams are down, totally loaded and all, then it sends a signal to the main control unit. Control unit understands that it has been configured. Then it gives a command. In fact, I will be discussing in my next lecture how FPGA functions totally, the hardware design. I will discuss in the next class.
Okay, sir.
So it gives a command then. So there are first is configuring the FPGA. So for configuring the FPGA, what happens? The control unit gives command to one controller. This controller sends the necessary signals to the square PROM where bit streams are stored. Then the bit streams will be downloaded from square PROM to FPGA. That is called configuration mode. Once the configuration is complete, then a signal will be sent to the control unit from the controller. Once the control unit understands that FPGA has been configured, it sends a command signal, execute. This function starts getting executed. Then if it is required that when it is doing a particular function, during that time it is required to download some other bit stream, okay, dynamically, that also can be done under the command from the control unit. So a control unit must be required.
Okay, sir. Thank you, sir. That's why we have the Spartan 7 in our university, Spartan 7 board. When we have downloaded the bit stream, then we have to select one mode. There are
Yeah,
two
yeah,
modes. One is called JTAG mode, and
yeah,
another is called PROM mode.
yeah.
We
PROM
have to
mode or
select
yeah.
JTAG
Yep.
mode.
If you select JTAG mode, then directly from there, the bit streams will be downloaded.
Yes, sir. Okay.
Okay.
Yes, sir.
So anybody has any questions? So next day I'll be discussing in details how the whole thing is being done. Okay, PG. Then we'll go for this. Once it is over, then we'll go for AI architecture. So if there is no other questions, can we stop now? Hello.
Okay, sir. Thank you, sir.
Okay.
Thank you, sir. Thank you.